Hi. In this next set of lectures, we're going to look at some models of tipping points. Now, these are going to be highly nonlinear models in the sense that what happens is going to be that a small change is going to lead to a big effect. So instead of being sort of a nice linear thing like we've seen before, we're going to see abrupt changes, right, where the system tips at some point. Now, our goal here is to really try and understand in a deep way how tipping points occur and what is a tipping point and what isn't a tipping point. Because one of the things we're going to learn is a lot of things that look like tipping points really aren't tipping points. So let's get started. What is a tipping point? Well, imagine the proverbial case of a tipping point is the straw that broke the camel's back, right? So suppose I've got this is a graph of the weight of a camel, and here I'm adding pieces of straw, right? So as I add pieces of straw, the weight of the camel goes up in a nice linear way, right? The weight of the camel, I should put weight of camel plus straw, right? That goes up in a nice linear way. But if I were to graph the height of the camel, what would happen is the height of the camel would be pretty much constant as I add more and more straw until eventually the camel falls down, its back breaks, and then the camel becomes much, much shorter, right? So this point right here is where the tip occurs. So that's what we mean by a tipping point. One more piece of straw has a huge effect on some variable of interest, namely the height of the camel. Also, the speed of the camel as well. That would also tip. It would go from a positive number to 0. So people talk a lot about tipping points. Malcolm Gladwell a few years back wrote a book called The Tipping Point, which sold millions of copies. And when people talk about tipping points, they often mean kinks in curves. So if you look at housing starts in the United States, right, they're going up really nicely from the beginning of the new century up until about 2006, and then there was this big kink right here. And so people tend to say this point is a tipping point. And I'll actually argue that that probably was a tipping point. But then people look at things like, this is users on Facebook. This is a graph of Facebook users graph, and you see this thing goes up here. And there'll be people that say, oh, right here, 2008, that's the tipping point. I'm going to argue that's not true, okay? Same is true if you look at the world population. You might say, oh my gosh, look at that. In the 1940s, the world population took this big kink. It did kink, but I'm going to argue that's also not a tipping point. Same's true with Wikipedia articles. People say, oh boy, Wikipedia in 2004, this was really the tipping point. These are all cases of the graph having a big kink in it, but they're not necessarily tipping points. A tipping point is when a small change leads to a large effect. These processes that we've just looked at, Facebook, world population, Wikipedia entries, these are all cases of just exponential growth. And when you have exponential growth, you're going to get a curve that takes off, just like if I draw like, x squared or x cubed or x to the fourth, right? I'm going to get something that sort of goes like that, and you can convince yourself, ooh, right there, the slope seems to be changing really fast. Nothing tipped. That's just an inevitable process of growth. So one reason we want these models is to be able to make sense of what's a tip and what's not a tip. And we also want to ask, what kind of models produce tips, right? How can we get tips and when are we likely to see them? So here's what we're going to do. We're going to construct two really famous models, one from physics, one from epidemiology. The physics model is known as a percolation model. And many of you maybe own houses and you had to dig wells, and there's a question of, did the ground perk? That's what they say. Well, they're asking, did it percolate? So could the water sort of filter down through the ground, or was it too clay-like and would hold the water in? So percolation literally refers to, can sort of water make its way through a system, or like coffee percolating through coffee grounds. Then we're going to look at something called the SIS model. S stands for susceptible, I stands for infected, and S stands for susceptible again. This is going to be a simple model of disease, where you have this disease, you don't have the disease, you get infected, and then you don't have the disease again. Okay, so we're going to construct that. Both of these models will have tipping points. Then we're going to make a distinction between types of tips. I'm going to talk about direct tips. A direct tip is a situation where a particular action tips that same dimension, that same variable. So for example, in the context of a war, a battle might tip a war, from one side winning to another side winning, right? So it tips the same exact entity. Alternatively, there's a contextual tip. Contextual tip means something changes in the environment that makes it possible for something to happen. Okay? So a direct tip is where the variable itself changes that causes itself to tip. So it could be, people buying a particular product. It could be battles in a war. A contextual tip is something in the environment changing in such a way that it then causes the system to move from one state to another. I'm going to make a second distinction between types of tips. Remember we talked about these 4 classes of things that the world can fall into, right? It can be stable, right, like an equilibrium. It can be periodic, right? It can be random, right? Or it can be complex, right? These are sort of the 4 types of states a system could be in. Well, a system could tip from one to the other. So something could be stable and tip to periodic. Something could be periodic and tip to random. So we can talk about not only direct tips and contextual tips, we can talk about tips between class, right? So it goes from one class to another, and tips from within class. So for example, if a system tips from one equilibrium to another equilibrium, that would be a within class tip, right? Because the overall structure of the system hasn't changed in terms of how we categorize the types of outcomes we see. All right, so that's the plan. We're going to construct some basic fundamental models that produce tipping points. We'll show that a lot of things that people call tipping points really aren't tipping points. They're just exponential growth. And then we'll classify types of tips, right? We'll talk about between class tips and within class tips. We'll talk about direct tips, and we'll talk about contextual tips. Then we'll conclude with just a very short lecture on how you might measure tippiness. And this is some work I've actually done with a colleague of mine, P.J. Lamberson, coming up with some measures of how tippy a system is. Okay, let's get started. Thank you.